over all k prime not in the final queue, because those guys obviously still exist. Not. Where k prime is inserted at time greater than or equal to t prime. So basically I can turn the word deleted into the word inserted if I change t to t prime. And I also have to exclude the guys at the top. So we're looking at a particular time like here. I want to know who are the things that are deleted after that. Well, this is deleted, all these guys are deleted after. I'm going to rewind to t prime and say, well, you know, there are these guys that they survive. They obviously don't get deleted. But if you ignore the guys that end up in the final queue, the guys that get deleted after time t are the same as the ones that get inserted after t prime. That's the claim. Or actually, that set of elements is not the same, but the max will be the same. That's all I care about. I only want to know the max. The max among all the ones deleted here is this uppermost segment. And that's the same as the max among all the guys that are inserted after here. So it's really just a claim about this one being inserted after this bridge. I won't prove this lemma. It's just, you think about it for long enough, it becomes obvious. I'll leave it at that. Now we can do some data structures, because now we have something that we can reasonably hope to maintain. So maintaining bridges, one thing. Yeah, actually kind of important thing. So here's what we're going to store. We're going to store the current queue as a balanced binary search tree. Okay, that's not very exciting. The hard part is to figure out how Q now is changing at each step. But this will allow us to do arbitrary queries on the final result. We want to store a balanced binary search tree whose leaves represent insertions. So lowercase insertions. So that's all of the rightward arrows. And they are going to be sorted by time, not by key value. Okay, and I'm going to augment that balanced binary search tree with a fun value for every node in the balanced binary search tree. I want to know the max of all the keys not currently in the queue, or not presently in the queue at the end of time. That changes very slowly, so this is easy to maintain. Among all the keys that are inserted in the subtree rooted at x. Okay, that's basically this value which I want to maintain, but split up over a subtree. And so that lets me easily compute this value by taking the max of log n of these values at any time. Okay, then we store another balanced binary search tree where the leaves are all the updates. Again, they will be ordered by time. And they'll be augmented. In each node, I'm going to store a number, which is 0, +1, or -1. It's going to be 0 for an insert. This is at the leaf level, because the leaves correspond to updates. If that key ends up in the final queue. So those we just ignore. It's going to be +1 for any other kind of insert. So inserting a key where k is not in queue now. And it's going to be -1 for delete min. I'm going to store this, and we're going to have subtree sums. So this is fun with augmentation. Why do I do all that? Because if I store all these numbers, it becomes really easy to detect bridges. I claim. Yeah.
So is what we're moving towards is basically we know how the cascade will end in any given.
We want to compute how one of these cascades will end.
And so we just always maintain that information.
We're always going to maintain what's here. We can't afford to maintain this whole picture because it changes too much. But we're given this, we want to know the result of the cascade without having to do all that stuff in the middle. Yeah, that's our goal. And I claim, this is a lot of text, but I claim that this information is enough to do that in log n time. So let me try to convince you.
So are you storing several binary search trees?
I'm storing 3. I'm storing one that represents the final result. I'm storing one that's just looking at the insertions, and I'm storing one that looks at all the updates. I maintain all 3, and you can cross-link them all you want. Okay, I claim a bridge is now a prefix of updates summing to 0 according to this measure. Okay, because inserts and deletes, when they all cancel out, and if we ignore the things that finally end up there, the periods of rest, when no one is active that will eventually get deleted, that's exactly when everyone to the left has been deleted or will survive to the end. So these guys count as zeros, so we ignore those. Each of these corresponds to a +1, each of these corresponds to a -1. So these have all canceled out by now. And when this prefix sum, which is everything up to a given point, is 0, then that is a bridge. What this lets you do is if you have this binary search tree, you have some query time t, which corresponds to a leaf, and now I want to know what is the preceding bridge. I want to know t prime, the bridge preceding time t. Then basically I walk up this tree and find the preceding moment. I actually have to first walk down to compute all the sums. So hanging off on the left of this path are all these times in the past. I say, well, if the sum of all of those subtree sums, sum of all the values in those leaves, if that's 0, then we're already at a bridge. If not, I basically compute the preceding point where this sum up to that point is 0. And that should be relatively obvious how to do. It's a regular kind of walking up the tree. So in log n time, I can find the preceding bridge. Because I have all these subtree sums, I can do that by a tree walk. Okay. Then it just says here, and then you can compute the change to Q now. All right, how do we compute the change to Q now? We have to compute this max of all the keys that are inserted after time t prime. So this was the tree of all updates. And we have another tree, which is just the tree of insertions. And so if we cross-link time, so we find t prime where the prefix sum is 0. We map over to t prime here. And again, we get a root to leaf path. And now we look at all of the elements hanging off the right side. Those are all the elements that are inserted after time t prime. I just take the max of those. So I guess I didn't write it, but I need to store subtree. Oh no, I store this. Great, this is what I want. For every subtree, I want to know the max of the things in that subtree, but ignoring the guys that are in Q now. So I take all those maxes on all those subtrees, and I can find what element gets inserted into Q now in log n time. Then, of course, I have to update all this information. I don't want to spend any more time on this, no pun intended. You have to then queue out changes, and so you've got to update all these values and these values. But the claim is that you can do all that in log n time. It's not hard. Whew. Okay, that's priority queues. So I know that was a little bit tedious, but this is sort of, it's not quite the coolest thing we know how to do, but it was the first cool thing we knew how to do in the retroactive world. It's this nice borderline where looks scary, there are linear sized chain reactions, yet we can still deal with them in log n time. So not quite the worst case, but also not easy. So in general, if you want a retroactive data structure for your favorite data structure, you're going to have to think along these lines, see whether you can maintain something reasonable. Let me tell you briefly about other problems, other data structures that we've looked at and other people have looked at. So a simple one is a queue. First in, first out. First in, last out. One of those. Got stacks too, probably. You can do constant time partial retroactivity, log m time full retroactivity. For a deck, I mentioned this last time, where you can insert and delete from either end. We can do log n full retroactivity. For union find, you have a bunch of sets. You want to be able to take their union, and given an element, you want to know which set it's in. It's sometimes taught in 6046. Best thing we know is log m fully retroactive. Priority queue we already talked about, but is there a question? No. Priority queue we already did partial retroactivity, but what if you want full retroactivity? This is pretty much an open problem. Best thing we know is square root of m times log m. This is via, we have a general result that says if you have anything that's partially retroactive, you can make it fully retroactive at a huge cost of square root of m factor. So you could take what we have, make it fully retroactive. Full.
Is there any difference when you're talking about m? While you're talking, is there any difference? Is that an n?
N, I think, is supposed to be the current size of the data structure. I'm not actually sure what that means with a retroactive operation. I'll just make them all m's. I think that's safer. Other question? Or same one? Okay, good. Thank you. Okay, let me tell you about the most important problem in this field. This is actually what motivated us to define retroactivity, which is a particular problem, retroactive successor. So successor problem is I want to be able to insert and delete keys in one dimension, and given a query key, I want to know what is the next key greater or equal to it. This is something you can do in log n time with a balanced binary search tree. There's lots of other ways to do it, which we will get to later in this class. But what if I want to do it fully retroactive? Okay, partially retroactive is really easy because this is a search problem. So I can definitely do log m partial retroactivity. Okay, in fact, it is I just use a regular binary search tree or whatever. In fact, it is a decomposable search problem. So I get full retroactivity, no problem, but I pay a log factor. So I get log squared m, full retroactivity. And so that's where we left it back in 2003. But there's a new result, which is that you can actually get log m without the square, full retroactivity. This is a complicated result. It's by Giora and Kaplan from 2009. It uses fun techniques like fractional cascading, which is next lecture, and Van den Bois, which is lecture 11, and various other tools. So it's a little too advanced to cover now, but it's cool, and it has lots of applications in geometry, which we will be talking about next class. So hold your breath for that, I guess. Yeah. I want to go to one last topic, which is a different kind of retroactivity. Yeah. Non-oblivious retroactivity is introduced by Akar, Blelek, Tanglongsen in 2007. And it's basically answering the question, what about my queries? So we have this timeline of updates, and we've done various operations on our data structure, which are the updates, and we've considered how those can be changed. And then with queries, either we're querying at the end or querying in the middle. But we're always getting sort of instantaneous, as the timeline exists right now, here's what the result of your query is. But what if I want to do, if I really, normally when I use a data structure, I do some updates, I do some queries, I do a combination of these things. And to make life worse, when I do a query, the result of that query probably influences what updates I do in the future. So real use, I also call that the algorithmic use of a data structure. Results of queries influence updates. What updates you're going to do. Okay, now this gets a little dicey because what does influence mean? We don't know, because that's the user somehow depends on these results. So, but non-oblivious retroactivity is trying to deal with this issue. Can we get something reasonable? So what we'd like to do is say, oh, I now add an update over here retroactively. So their updates are the same in some sense. You can retroactively insert and delete updates and queries now. I'd like to know, well, did the result of this query change? Maybe you can show at the data structure level we can tell, did that query result change? Maybe this one changed, but this one did not. What we'd like to report to the user is, what is the first query that changed? Because that's like the first mistake that you made. Like, oh, retroactively, oops, I should have deposited $100 back here. And then, these queries which were checking whether the balance was positive or negative, some of the results might change, some of them might not. If they change, then the algorithm has to, it doesn't have to rerun these operations, because that's what retroactivity buys for you. But it has to say, oh, well, now this query has changed. And then you have to rerun the algorithm from that point. But not necessarily entirely. You look at that and say, oh, did that query actually change anything? This is now the algorithm. So, oh yeah, instead of this update here, I would have made a different update u prime. Well, that's good. We know how to do that. That's a retroactive update. So I can delete this operation retroactively and insert this one. So in general, what we assume the algorithm does is it finds it looks at the first error, which is reported by our data structure, and then it may make various changes from that point onward, but always monotonically left to right, as if it was rerunning the algorithm, but just changing what needed to change until all the errors are resolved. All the queries have been corrected to their right answers. Then it can do whatever it wants. Then it can do a retroactive operation anytime in the past. Okay, so this is an assumption. Assume once there's an error, that the algorithm makes changes, retroactive updates from left to right. And also going to assume that it does it at times less than or equal to all errors. So in general, if you have a timeline, then there's some errors where bad queries were done. Naturally, you would go right here and fix the first error, because that may influence other errors. Okay, and maybe you have so then you make that change. Maybe then that causes some other changes right after or somewhere in between. But then I don't want to make a change here because that would be depending on this result, which was incorrect. So first you have to fix this. Okay, so you keep going to the right and you visit all the stars. That's this assumption. This is a very different kind of retroactivity. I would say it's more about maintaining this exact picture of what's happening, but being able to teleport over the uninteresting stuff. So in this picture, if we're doing priority queues like this, when I make this change, well, that query changes, that query changes. You know, the delete mins, the mins that they're deleting change. So here they were just updates. But if there's also a query here, which is what is the min, then all of these query values would change. So you're forced now to pay for that. So in some sense, it gets easier, I would say. For a lot of problems, this kind of retroactivity is easier. But for many problems, it's also more useful. So their example is, what if you want to do dynamic Dijkstra? So you have Dijkstra's algorithm, and then you say, oh, actually, this edge weight was wrong. So you run Dijkstra's algorithm once. You've got a priority queue in there telling you which vertex is next. And then and now you say, OK, I changed this weight at the beginning of time. I don't want to have to rerun Dijkstra entirely if nothing changes. Maybe that weight was completely irrelevant. Well, if you just do a retroactive update and see, did any of the query results change? If they didn't change, then great, you have the right answer. If they did change, the results change. And so you have to know for every wrong query that, oh, I really had to change the shortest path weight. It's not this, it's now this. But hopefully, you will only have to change a very small amount if your graph didn't change in a big way. So it's hard to prove results about that, but at least this would let you dynamize almost any algorithm that's using the data structure. So it's easier but useful for that kind of transformation. Okay, let me give you an example, which is priority queues. There's a bunch of results in their paper, but for symmetry, I'll tell you about priority queues. This will look completely different, so don't worry. Operations, well, the visual picture is the same, but the data structuring is all completely different. They can do all these things in log m per retroactive operation. Now there's no notion of full and partial. It's just non-oblivious retroactivity. I didn't write it here, but the data structure always maintains what is the earliest error currently. So maintain the earliest in time error. That error is a query that used to return one result, now returns a new result. Okay. We have a similar picture. So I changed things a little bit. I didn't cheat. It's just a slight discrepancy. For regular retroactive, insert and delete min were more interesting because then there were chain reactions. In this world, you don't have to combine delete and min. You could consider delete separate from min. Because now updates are allowed to depend on queries. So maybe you compute a min and then you decide to delete that thing. And if the min changes, well, then the thing that got deleted might also change. That's the algorithm's choice, what to do. So in this new world of insert, delete, and min, which is slightly more general, if you look at an item, it gets inserted at some time, might get deleted at some time. Sometimes it might go off to infinity if it never gets deleted. Okay, this is our new picture of the priority queue over time. So again, this is the time axis. And this is the key value. So you have some inserts, deletes. They all correspond to points in here. And then you have min queries, which maybe I will draw in red. So min query would be something like this. Give me what is the lowest segment at this time. Okay, so that's my sequence of operations is a projection onto time. So there's this thing, then there's this query, then there's this insertion. Then there's this deletion, then there's this deletion, then there's this query, min query, then there's this insertion, then there's this query, then there's this deletion. You get the idea. But this is a way to two-dimensionalize that picture. Sorry? You can delete without a query in this model. Yeah. Make our life a little bit harder. Now, what we need to support are insert, capital insert, and capital delete, retroactive insert and delete, of all three of these operations. Before it was just updates. Now we can insert and delete queries. A little harder to think about, but it can be done. So for example, I'm not going to do all the cases because there's a lot of them. Let's say I delete this deletion. Okay, that means that this will just go to the right. Okay, that's bad because it changes all of these queries. All these queries are now incorrect. We're just going to keep the picture like this and remember that there are errors, and we'll be able to maintain at every moment what is the next error. The errors are these crossings. Crossings are bad. That means you have the wrong picture. But we'll wait for the algorithm. We'll tell the algorithm this is the next crossing, and it's going to have to fix it by, say, deleting that query and then reinserting it. Then it will get the correct result. But it might do other updates meanwhile. So let's not try to fix them all now because they may change. Maybe they'll decide to reinsert a deletion here, which would do that, and then erase all of those crossings, if we're lucky. You might also insert an insertion. That's basically the same as deleting a deletion. You get a whole bunch of crossings. Then so inserting an insertion and deleting a deletion are about the same. So the other case is inserting a deletion or deleting an insertion. So inserting a deletion. Good. Let's say that I insert a deletion here. So now suddenly this thing ceases to exist. All of this is gone. We get not a crossing error, but we get what I'll call a floating error, which is that these guys are currently returning something there's no segment there. Okay, so we can get crossing errors and floating errors. I want to give you enough of this data structure to show that actually you use these data structures to solve it. So in that sense, it's actually not that much easier. I said it was easier, but we're going to need a retroactive successor in order to solve this problem. Okay. Some invariants. Man, who uses this colored chalk? It's so hard to erase. Let's say I want to maintain the lowest leftmost crossing. So in this picture where I have a bunch of crossings, this is the one I want to maintain, the bottom left one. Now there's a bit of a subtlety here, which is do you minimize y coordinate and then x coordinate, or vice versa? It turns out these are the same thing. I don't want to prove that here, but because of this assumption that we're always proceeding monotonically left to right, we have a nice invariant that if you look at all the crossings, they involve segments that start to the left of all errors, because all the changes we've made are to the left of all errors by this property. And so it's really just a whole bunch of rays coming in from negative infinity on the left, and a whole bunch of rays coming from minus infinity on the bottom. Sometimes the rays stop, but if you look at where they cross, there's a uniquely defined bottom left corner. Okay, so that's this picture. These rays might go different amounts from either side, but there's a single lower left corner. So we're going to maintain that. And we're also going to maintain the leftmost floating point floating error on each row separately. So in each horizontal line, like here, we'll maintain that there's a floating error here for this row, but we won't figure out that one till later. That just saves the work we have to do. Okay, now let me show you an operation. Let's do insert min. So I'm going to use x for time here because it's a little bit more intuitive. X coordinate is time. Suppose I want to insert a query. This is actually an easy case because there's no chain reactions here. It's going to be correct because I'm doing the query right now. But this is basically a fully retroactive query. I'm adding a new query, and I want to know what is the first ray that I hit. How do I solve that? So what's going on here is I'm basically manipulating these line segments. I mean, the red lines don't really affect this query. They just might be incorrect, but I don't care if they're incorrect. I just want to know, for this query, what is the lowest segment? So really, I have segments. They're changing, inserting and deleting endpoints of the segments. And I want to know, from below, what is the first segment that I hit? This is called upward ray shooting. Or vertical ray shooting, I guess would be the normal phrasing, but I want to be a little more specific, not downward, upward, among dynamic segments. This is a well-studied problem. And conveniently, it can be solved in log n time per operation. So you can modify segments and do upward ray shooting queries in log n time per operation. But you already knew that. Good, you're nodding your head, because that is retroactive successor, if you think about it. A retroactive insertion operation in the past is like, it's fully retroactive successor. That's this result. Inserting an insertion, that's like creating a new left endpoint of a segment. Inserting a deletion is like creating a new right endpoint. Deleting a deletion or deleting an insertion is, you could use that to move the endpoint. So that's exactly dynamic segments, horizontal segments. And then shooting a ray is, in general, if a general ray shooting query is like this, I can be not from minus infinity, be at an arbitrary point and ask, what do I hit upward next? That is like, at this time, doing a successor query. Okay, now this is a special kind of successor query because it's always from minus infinity. So you might be able to solve it easier, but in particular, you can solve it using this result. So regular retroactivity helps you do non-oblivious retroactivity. Cool. Out of time. So I will just say the other cases are similar. There's one other thing you need to do, which is in addition to upward ray shooting, you have to do rightward ray shooting because of things like this. If I delete this deletion, I want to know what do I hit next. So that's a rightward ray shooting among dynamic segments, which all happen to start at minus infinity. So it's again, it's dynamic ray shooting or successor queries, but in X instead of Y. So with those tricks, you can do all of the cases of inserting, deleting insertions, inserting, all combinations of those things.